Okay, we want to stay with this drug example, but now we want to think about the example in the terms of equilibrium, their stability, and cobwebbing. And so an equilibrium for a difference equation, xt plus 1 is f of xt, is a value, x hat, that satisfies x hat is f of x hat. So what this means is if you plug in x hat to f, it just gives you x hat back. It's asymptotically stable if solutions that start near x hat go towards x hat, but it's unstable if solutions that start near x hat move away from x hat. And so we can ask, what are the equilibria for the equation that we've been looking at, which is Cn plus 1 is 0.3 Cn plus 0.2. We'll call that f of Cn. And what is their stability? Okay, one way that we can calculate then is just to plug the C hat into this equation here. So we have C hat is 0.3 C hat plus 0.2. And if we take the 0.3 C hat to the left-hand side, we have C hat minus 0.3 C hat is equal to 0.2. So 0.7 C hat is equal to 0.2. And C hat is 0.2 over 0.7. This is exactly the value that we found that C went to as n went to infinity, 2/7. What this means biologically is that if the drug concentration is 2/7 on one given day, it'll remain at 2/7 for all future days. So to try to analyze this system a little more, I'm going to use the method of cobwebbing. And here we start with a value on the x-axis, such as C0 is equal to 0, and then we move up to find the value for C1, and then we reflect across to the 45 degree, and then we can write C1 here. And then we go up to the function, and then we reflect across again, and then we continue. So this will be C2. And if we start with 0, we can go in this direction. If we start with 1, we can start over here and move up to the function, and then over to the 45 degree. And then this is going to be our C1, and then our C2, and so on. If we take these all the way across to the graph here, we see that our C1 here moves over to here, our C0 moves over to here, our C2 moves over to here, and so on. Here, our C1 goes to here. We start at 1, and then we come down. If we take this equilibrium value and draw it across, we get the value 2/7 here. And so this graph that we're drawing here is very similar to the graph that we drew when we calculated the solution explicitly. But this is a graphical method for solving the equation. The power of this graphical method is immensely greater when there's a nonlinear function that we're trying to solve as opposed to a linear function. We've used the linear function so we can tie it back to what we did in chapter 2. But if there's a nonlinear function, then the graphical method is a very handy way of determining what's happening without having to do numerical computations. And as we can see, if we start on this value here, C0 equals 0, we're moving towards this equilibrium point as time goes forward. And if we start at C0 is equal to 1, we're also moving towards this equilibrium point here. So this point is asymptotically stable. We see this also with the diagram here. Regardless of whether we start at 0 or 1, we're moving towards this equilibrium value of 2/7. And so we can understand this drug problem both with the formulas from week 2 and with the cobwebbing approach. And the purpose of this video is to try to make a tie-in between these two approaches. The next video, we're going to consider nonlinear dynamics for the cobwebbing and look at all the interesting outcomes that can happen.